Hey guys, so this is the last video I'm recording right now for torque, and this is really going to hit on torque not at 90 degrees. So this is worksheet 3.3. As you get into that worksheet, you're going to start to see some really weird stuff that's not like what we did before. Because in the previous examples, you'll remember we had like teeter-totters and seesaws and things where everything's at nice 90-degree angles, like Jen and Eric's store here. But on this part and on worksheet 3.3, you're going to see that we have torque not at 90 degrees. And so if we're trying to figure out what happens when a force acts in a direction other than directly perpendicular at that 90-degree angle to the body, basically we're just going to have to add one little thing. And when you've looked on your formula chart, I'm sure you've seen that the torque equation is not actually exactly like what we've been working with. So let's just jump in with an example and we'll kind of talk about that. It says here we have a 2.2 meter long 50 Newton uniform beam that's attached to the wall by means of a hinge. That's this circle here. And so it says that attached to the other end of the beam is a 100 Newton weight, and a rope also helps support the beam as shown. And so in a more realistic scenario, instead of hanging my sign straight down, I'm probably going to pull it over to the side and tether it to part of my building or whatever. And so they want to know two things here. One, what is the tension in the rope? And two, what are the vertical and horizontal components of the supporting force on the hinge? And so if we think about this tension being provided over here, that's going to be pulling away from the wall a little bit. And we're going to have some forces on our hinge that we need to be thinking about in order to support the system with true equilibrium. And so if we first jump to this box here and we kind of think about the forces that are acting, our free body diagram would look something like this. We could just kind of redraw our hinge real quick in our beam. Ooh, that's ugly. If we think about the tension over here at the angle that they gave us, which was 30 degrees, then there's really a component of that tension up here that's perpendicular to the beam, and there's a component of the tension that's parallel. Kind of like when we were doing inclined planes, we would have a component that was parallel to the inclined plane and a component that was perpendicular to the inclined plane. They do tell us the distance, so I guess I can add that to my diagram here. The distance of my beam was 2.2 meters to the end. And then we know that in the center of the beam, we would have a gravitational force vector going down. We'll call that FG1 because the beam itself has to be supported. And then in addition, I'm going to draw a second kind of longer vector arrow over here for FG2, which represents this weight at the end of it. And so that distance here from the hinge to this first would be 1.1 meters, since we're assuming we're using a nice uniform beam. So the big thing to notice here is that if we break the tension into component forces, then the parallel component doesn't actually do it doesn't contribute to the torque, either in the clockwise or counterclockwise direction. It is simply providing a force outward, which would have to be opposed by a inward force on the hinge right here. And then in addition, just like before, we know that the hinge is going to have to be supplying some force up to counteract the two gravitational forces. So you could think almost as a force on the hinge, FHY, and the force on the hinge, X, which means that overall my net force vector is somewhere here for the hinge. It's actually being pulled away from the wall in the X direction, and it's being pulled up into the wall in the Y direction in order to counteract the tension. So if we scooch down, we can actually find and do this. But the big thing to think about, we're not using tension X and tension Y. It's going to be better and more helpful for you to instead, so we're not doing this, instead try tension perpendicular and tension parallel. And so the reason we're doing that is because, as we're going to see on the backside, sometimes examples get a little bit complicated. But then the last thing to fill in here before we work the problem is whenever we're calculating the torque on a body, in this case on that beam, we always use the perpendicular component of the force. Okay, so let's do it now. Step one is just like it always is. We are going to write a torque statement, and we're going to assume it's in equilibrium because that's what they told us. And so for in equilibrium, that means torque clockwise is equal to torque counterclockwise. That's always a starting point. And by writing that, you're probably getting some points. So looking back up at our free body diagram, in the clockwise direction, think about like how a clock is moving, we would have FG1 and FG2. So I would put FG1, D1, plus FG2, D2, which is equal to, in the counterclockwise direction, the main thing supplying force is the torque. The pivot, we did talk about having forces, but if the distance to the pivot is 0, we know torque is equal to force times distance, then in terms of our torque, the pivot is not providing any torque. It is providing a force, it's not providing a torque because the distance from the pivot to the pivot, it is the pivot, so that's going to be 0, which means it's 0 torque. So the only thing providing counterclockwise torque, opposing the clockwise torque, was the tension. Specifically though, it's the tension perpendicular, and we'll call that times d2. And we can still use d2 because both of these distances are the full length of the beam. So here we could rearrange. Tension perpendicular would be equal to, we would have Fg1 d1 plus Fg2 d2 all over 2.2 meters, which is our d2 as we said. And so if you plug in your numbers, you get, they gave us the weight 50 newtons and 100. So 50 times 1.1 plus 100 times 2.2. If you want to write it in, I can. So 50 times distance 1 was 1.1 meters plus 100 newtons times d2, 2.2 meters, all over 2.2. You can't just cancel these because you would have to cancel it out of this one too. Go to math jail. That gives us 125 newtons. And so we've just found the perpendicular component of the tension. And so if we think about that, back up on our diagram, let me redraw. We had a tension here, and this is at a 30-degree angle. So if I just found this component, you could think about this has to be a 90-degree angle because this is the tension perpendicular, this would be the tension parallel, which previously we drew up here. That means this has to be a 60-degree angle because this total thing has to be 90. So if I do the cosine of 60, that would give me the adjacent, which is this guy here, over the hypotenuse in order to actually find what the tension in the rope is. And so the cosine of 60 would be equal to the adjacent, as we just said, t perpendicular, over the tension, which means tension would be equal to 125 newtons, my t perpendicular that we just found, divided by the cosine of 60, which is 250 newtons. So the tension in the rope is actually stronger than one of the components, which makes sense. The hypotenuse is always longer than either leg, and it's 250 newtons. So we're done with part 1. However, in part B, they also wanted to know what was the vertical and horizontal components of the supporting force provided by the hinge. So now we found the tension in order to establish our net torque of 0. And so thinking about the forces on the hinge, let's scooch it down a little, give myself some room here. I'm going to redraw my hinge once more. So we have our hinge and we have our force. We know that there's Fg1, Fg2, and then tension. I'm going to go ahead and draw it like I just did with the 60-degree angle, tension perpendicular, tension parallel. So as we mentioned, there's got to be some kind of x and y forces on my hinge. So we're just going to call those force y and force x. And I like to put a big X because that's my hinge. And so thinking about that in the y direction, my sum of forces y must be force y from the hinge plus tension perpendicular minus Fg1 minus Fg2 all adds up to 0. Which means that the y force on the hinge is simply Fg1 plus Fg2 minus the tension perpendicular. And so these are all values they gave me. 50 plus 100 minus 125, which is 25 newtons. Okay, and you can look back up ahead to get the values there. So that's easy. We're done there. In the x direction, though, I'm going to change color. So here, thinking about this x force, the only thing that is opposing that force would be this parallel component of the tension. Those are the only two x forces that even exist. And so it's kind of weird, but if you think about this being pulling out to the right, that's really our positive force. So we would have tension parallel minus the force X equals 0, which means the tension parallel is equal to force X. Now, we didn't find tension parallel up ahead. However, we did find the overall tension. And so we know that the parallel component, because we know that this tension is a value, we could just do tension times the sine of theta, where theta is 60 degrees here, would be equal to F sub X. And so that's just going to be 250 newtons, that's my tension, times the sine of 60, which is 217 newtons. So just checking our numbers real quick, 217 newtons is less than 250, that's good, because this is a component of the overall 250. My 25 Newton Y force on the hinge, and then if I wanted to actually find the overall force of the hinge, just resolving those two vectors, I could do Pythagorean theorem, since that's a nice right triangle, to find the actual value of the overall hinge force. But they told me in the problem to just find the vertical and horizontal components, so we're done. Okay, let's do one last thing. On the back side of this notes page, it says in big bold letters in a scary box, rule not to break lest ye be broken. It's not a threat, it's a promise. So this says, when we find the torque acting on a body, we must always use the component of the force that is blank to the blank blank. What are we putting on the blanks? You might have guessed it. We have to use the component that is perpendicular to the beam. And so I'm going to work on a separate video of this example if you want to watch it. Otherwise, you can stop the notes and you can start practicing. If you practice and you find that you can't do one of them, you can always come back and watch this example, and then you can continue working on your 3.3 worksheet. Remember, on the 3.3, we're just doing the odds. So make sure you like, subscribe, and follow. LOL, JK.